Thanks very much. Very tough act to follow. Thanks, Mark. That was epic. So this was... I love working in existing buildings. They're challenging, they're interesting, but existing hospitals takes things to a whole nother level. So I thought this particular project, it was up at the Cairns Hospital, warranted a bit of a sharing exercise. We're replacing the chiller plant in the Block B building within the hospital. So I'll go through some of the project specifics, some of the challenges we faced, the plan we put in place to address some of those challenges, and then the gold dust is the lessons learnt that came out of the process. Not all of those sort of topics are things that we had issues with, but I think they're all relevant in the context of a chiller plant cutover. So here we go. So the design was done by Arup. Wattpac were the main contractor and VAE did the mechanical services. In a nutshell, we had to replace 5 of the existing water-cooled chillers with 4 new water-cooled chillers. You can see the plant space there. It's very, very tight in an existing plant room. There were 5 existing cooling towers and we were reusing those. They were replaced in 2017, so it didn't make sense to pull those out. Replacing all the pumps, valves and some new ventilation systems. The 2 mechanical services switchboards got replaced as well, along with the BMS panels and new controllers, so complete upgrade on that front. And 2 new active harmonic filters that went in, 1 on each of the main mechanical switchboards. So off the bat, some of the challenges we had to work within. During the project, we had to maintain the chill water supply to the hospital. So that was interesting. At least 3 of the chillers needed to be available at all times, and of those chillers we needed to provide at least the duty capacity on generator supply. The spatial coordination was incredibly difficult, so kudos to Wattpac for managing that. But effectively that meant that we had to break the project into 4 discrete stages, so each stage was 1 chiller, and we needed that chiller back up and running and stable and reliable before we even touched the next chiller. So basically taking a chiller offline, lifting it out, putting the new one in, sliding it into place, commissioning it, and then doing that all over again 4 times. We were reusing the existing condensed water cooling towers, but we had a change in temperature. We had to get more capacity out of the existing plant, so that had some challenges. And because we had 4 chillers and 5 towers, obviously the alignment of plant became a bit of a challenge and required some focus. At the same time, there was an HV project going on, so that project was supposed to finish prior to us finishing. I believe it's still going, so that didn't eventuate. And it caused a lot of, I guess, difficulty around planning where supplies came from for our switchboards, and in the end it delayed those power supplies and we had to duck and dive. And obviously being in Cairns, it's an open plant room, condensation was everywhere. So the plan started with validating everything we could about the existing chill water system, all the supply and return chill water temperatures, decoupler flow rates, staging, total capacities, all that sort of stuff. Not just as a DLAP, but also to work out if there were any opportunities to improve the system performance from what it was, to sort of help us in the future. A big focus before we even started ripping plant out was the sort of staged commissioning and handover process and the commissioning management side of things. So we made sure there were clear acceptance criteria for each cutover so that we had confidence that before we moved on, everything was reliable and stable and we could sort of leave it in its place. And that included making sure we had time between the stages to watch it operating with the existing plant before we sort of cut over the next chiller. And with these existing systems, especially the older ones, there's always a few myths floating around. It can be anything from something really weird that's a bit of weird kit that's operating in a weird way. It can be a control strategy. So in our case, it was the expansion system. When we got there, we had a closed tank, we had an open tank, both were isolated. So we were scratching our heads. Apparently that was because there was a leak recently. But what we ended up finding out was that this central plant is connected to another central plant on Block D, and that is hydronically connected, and that's where the system expansion tanks were. So we ended up going and validating the performance of those tanks so that we knew, based on our height, we were okay. So what did we learn? The focus on commissioning planning was absolutely paramount on this job, and I think it set us up for success. So we agreed with WAPAC and VAE exactly what they needed to do before we started functionally testing and before we went into that sort of operational monitoring. So that included pressure testing, flushing the pipework, chiller commissioning, pump commissioning, BMS point-to-point testing, sub-main circuits. Everything was documented, submitted, reviewed, and then we went into a sort of scenario testing. So we all spent a day on site putting the new chiller through any potential scenario we could think of, making sure it was staging properly, making sure that it could accommodate fluctuations in condensed water temperature, playing around with decoupler flows, and importantly, going through failure mode testing, so isolating pumps, pulling out sensors, shutting off power to various things to make sure the next chiller staged on, and we got an alert or an alarm. So I can't overstate the importance of that process. Unsurprisingly, condensation up in Cairns is a bit of a problem, especially if you're trying to replace insulation on pipework that is on a live system. So ambient conditions with wet bulbs to 27, chill water pipework at 6 degrees, no surprises. So VAE came up with some pretty unique ways of addressing that and trying to sort of isolate and condition various spaces so that they could dry and lag pipework. I'm a big advocate of conditioning plant rooms in the tropics if we can, understanding this was an existing plant room, but it does get around a lot of the issues you can see on a regular basis. And you can't lag everything to the point where you'll never get condensation forming. There's always going to be binders or valve handles or something that's going to sweat. And that could be dripping on electronics or controls or something like that. It could be tracking underneath the insulation, causing pinhole leaks. So it is something that needs to be considered. Something that I've started doing is I bought a little thermal camera that you plug into your phone. It wasn't super expensive, but I'll take it to every site inspection now because you can immediately see whether your installation is performing or whether it's been compromised. So this image wasn't from the hospital, but it shows how valuable that sort of assessment can be. The other thing is that pipework and insulation have operational lives, so they're not going to last forever, and we need to start sort of tracking or at least making observations about the condition of these assets over time. So non-destructive testing of some of the pipework systems is always a good idea. Maybe after 15 years, you do a sort of a 5-year sample of the worst case, coldest or highest or lowest sort of velocity areas to just get a baseline for how your system is performing. So ventilation in plant rooms is a bit of a no-brainer, but I think we need to move away from having just a basic square metre, sort of litres per second per square metre application of ventilation. Understanding exactly what equipment is going in and how much heat rejection it requires is really critical. And if that's for refrigerant clearance after a leak, then we need more than likely low-level extract because all the synthetic refrigerants are typically heavier than air. These units are the harmonic filters, and they put out a ton of heat, probably 8 to 12 kilowatts per unit. So if that's in an enclosed switch room environment, that's obviously going to be an issue, and we need to address it. And we are seeing more and more power electronics and sort of sensitive equipment going into plant rooms on chillers and controllers and things like that. So filtering the supply air into plant rooms is going to extend the operational life of some of that equipment and prevent the dust building up over time. So, as I said, we had 2 harmonic filters that were being installed on this job. Due to the HV project and the implications of that, the intent was originally that each mechanical switchboard was fed from a different transformer, so each harmonic filter was on a different low voltage network. That didn't end up being the case for a period of time. We had the 2 harmonic filters connected to the same LV network, and these filters can operate in parallel, but they need to be set up that way. It needs to be a master-slave relationship or peer-to-peer. If they're both connected to the same network and you haven't got that arrangement, they're going to see the same distortion and try and inject a corrective current to mitigate it, and you'll lose control and end up with more harmonics than you started with. I guess the other thing, I'm a big advocate of putting the harmonic filters on the mechanical switchboards as opposed to what typically gets done around specifying chillers with harmonic filters. In most cases, when it gets specified with an active filter, it'll get value engineered off and they'll put a line reactor or something in. They don't really serve the same purpose. The line reactor is to protect the VSD. The harmonic filter is to sort of look after the network. So by providing these filters on the MSSBs, we're not only dealing with potential chiller harmonics, we're also looking at EC fans and any other VSDs on the network. It also allows you to select what make and model of filter you're using, so that you can sort of roll it out across different parts of the hospital. So yeah, lots of benefits to that, but this basically, I wanted to illustrate the impact of the blue line is a typical unfiltered supply from a VSD. If you add a line reactor, you get the orange line, which is a little bit better. But the green line is what we're really chasing, more sinusoidal, less noise. So that's sort of the impact of these types of devices. From an MSSB and BMS cutover methodology point of view, as I said, we were impacted heavily by the HV side of things. But I think generally we overlook the redundancy side of these bits of kit. We're happy to put in extra chillers, extra pumps, extra cooling towers, but when it comes to the power supplies and the BMS panels, usually we're not applying the same level of redundancy to those bits of kit. To be fair, the image on the left is a work in progress. That wasn't the final product. But so I think if we might put we're very good at putting controllers per item of plant when it comes to BMS systems. But if we are powering all of those controllers from a single 24-volt transformer, then we've got a single point of failure. So we need to really applying the same logic to those control panels and trying to pick out the single points of failure. And if we can do that, then we're going to have a much easier time cutting over networks in the future. It's never easy to try and cut over a BMS panel when everything is basically in the one panel. The other nice thing to have would be on new projects, if we've got a BMS panel in place, making sure we've got space next to it, because at some point in the life of that system, you're going to have to replace or cut over the BMS control panel. And having space next to it is going to make your life a lot easier. It's going to avoid having to put a terminal strip box somewhere and then cabling to another location. So where possible, providing some real estate next to and around mechanical switchboards and BMS panels is going to future-proof your installation. So key takeaways, commissioning planning is key. It was really the backbone of the success of this project. And we didn't have any significant failures of the chillers that we did hand over. For critical infrastructure, anything that's heavily staged, we need to make sure that there's a clear set of rules, clear acceptance requirements, and everyone's sort of working towards the same thing. You can't go back to some of these areas to sort of finish or fix off. So that was a big part of this one. Considering condensation in plant rooms and I guess obviously not running any pipe work above electronic equipment, regardless of whether it's insulated or not, because at some point in time you could get tracking of condensation on that pipe work. Looking at insulation and pipe work as a life cycle sort of assessment as part of your assets, and making sure you're considering particularly the insulation side of things. In most installations we go into, you can find at least a few examples where the vapour barrier has been compromised and you've got sort of sagging or under insulation corrosion. Active harmonic filters, I hope we start to see more of these get applied to the bigger infrastructure sites. I think they're a useful asset. Just make sure we have provision to deal with the heat that they're going to produce. On the BMS and MSSB side, making sure we're applying the same level of redundancy to that equipment as we are for the rest of the mechanical services. And be a mythbuster. If you hear any rumours or hearsay about weird things happening, then it's always satisfying to solve a mystery. The worst thing that'll happen is you'll learn something. So that was just a few before and afters of the chiller plant room. So turned out pretty neat, I think. I think I've got time for questions. Do I?
Hello? Oh, thank you. Yes, you do, but I don't have any on my iPad. So does anyone have a question they want to ask? Oh, I'm just going to go down here so we can all hear. All right.
Yeah, Aaron from Children's Health. Just wondering, if you do this project again, what would you do different? Thank you.
The mechanical switchboards were probably the biggest, or caused the biggest amount of grief. So I think trying to split those up a little bit more. We had two, the requirement was for N+2 in the plant. We only had 2 switchboards, and that's the way it was originally. But only having 2 switchboards meant that we couldn't technically achieve the N+2 requirement. So trying to work out how we did that, and I guess for the next time, if we had 3 or 4 boards and if we had space, we could have broken it up a little bit more to provide that level of redundancy. The BMS was also a bit of a problem. Because we didn't have the new mechanical boards, we didn't have the new BMS controllers, so the new chillers were sort of being controlled from the old BMS. We didn't want to go and completely set up a new control system on old hardware, but we needed some level of control to stage chillers on or off, and the chillers themselves looked after the condensed water pumps and the chill water pumps. So during the project, until the very last cutover, we had quite a lot of decoupler flow. It was sort of 80 to 100 litres a second through the decoupler. That's sort of almost a fixed flow because we just didn't have that extra level of control that we would have had if the BMS was available.